Alright, so in this video I'm gonna be explaining another important article with the title ASAP, Adaptive Structure Aware Pooling for Learning Hierarchical Graph Representations. This AAAI paper in 2020 from Bangalore. Graph neural networks have been shown to work effectively for modeling graph structured data to solve tasks such as node classification, link prediction, and graph classification. There has been some recent progress in defining the notion of pooling in graphs, whereby the model tries to generate a graph-level representation by downsampling and summarizing the information present in the nodes. Existing pooling methods either fail to effectively capture the graph substructure or do not easily scale to large graphs. So we proposed SAP, a sparse differentiable pooling method that addresses the limitations of previous graph pooling architecture. And it utilizes a novel self-attention network along with a modified GNN formulation to capture the importance of each node in a given graph. Again, this paper is about node scoring. The approach that it uses for this hierarchical pooling is node scoring. So it also learns a sparse soft cluster assignment for nodes at each layer to effectively pool the subgraphs to form the pooled graph. Through extensive experiments on multiple datasets, we motivate the choice of the components. So there are three contributions that they propose: master to token, a new self-attention which is better suited for global tasks like pooling. You see the overview of ASAP. First, you have input graph, for example, graph of a molecule, social network, anything. Input graph. Then you have ASAP initially clusters, one hop, a neighborhood, considering all nodes as like this cluster assignment. We only show cluster formations of nodes 2 and 6 as medoids. Cluster membership is computed using M2T attention. And then the clusters scoring using LEConf. Then we have a fraction of top scoring clusters are selected in the pooled graph. So even you're selecting only some of the clusters. And finally, the pool graph. Then you have the model which has ASAP, then GCN, ASAP, GCN repeats. And in the middle of these, you get the readout, because if you give the readout informations to MLP, you can find a label of the graph. So SACpool improve upon top K by using GNN. Top K scores nodes. You see different methods. But this is the architecture of ASAP that has all sparsity, node class aggregation, soft edge weights, variable number of clusters, as opposed to for example, top K. We don't have such variable, or even diff pool. First you fix your cluster assignment matrix, so it's fixed. But in ASAP it's very flexible, so it has variable number of clusters. Then self-attention is used to find a dependency of an input on itself. An alignment score is computed to map the importance of candidate C sub j on target query QI. In self-attention, target query and candidates are obtained from input entities. Then we have token to token, which selects both target and candidates from the input set. And then source to token finds the importance of each candidate to a specific global task, which cannot be represented by any single entity. And then they extend the receptive field from pooling operation in CNN to GNN3. So for cluster assignment, they consider each node V sub I in the graph as midpoint of cluster C sub H of that node, such that the cluster can represent only the local neighbors within a fixed radius of H hops. So for H hops, you have this ring, this radius. So this effectively means that the receptive field is H. This helps the clusters to effectively capture the information present in the graph substructure. So given a cluster, we learn the cluster assignment matrix through a self-attention mechanism. The task here is to learn the overall representation of the cluster by attending to the relevant nodes in it. We observe that both T2T and S2T attention mechanism do not utilize any intra-cluster information. So we propose a new variant of self-attention called master to token. In master to token, we first create a master query which is representative of all nodes within a cluster. For example, the master of here is MI, this node. So it's a representative of all nodes within a cluster. So it reminds me prototype learning in few-shot learning. Prototype network in few-shot learning. The same type of idea you can think about. And in this work, we will experiment the max master function because it combines and transform feature representation to find M sub I. This master query attends to all the constituent nodes using additive attention. Finally, the cluster representation is computed as a weighted average of X sub I, with alpha is this additive attention. So master is here, and you have some nodes, xj. So you get the idea of this is attending to different nodes. And then we have cluster selection using a different architecture. So the top K ranks, scores, and gives the indices of selected clusters. So similar idea for cluster selection. Then we maintain the graph connectivity. This is important because if you do some deletion or these things, you want to make sure that you haven't lost the graph connectivity yet. So to force that, following this paper, once the clusters have been sampled, find a new adjacency matrix. This is the new adjacency, this is the old adjacency. And of course, there are limitations of using GCN for scoring clusters. So the data sets, they use these Frankenstein, NCI1, protein, D and D. These are for graph classification. And they compare different methods such as diff pool, sag pool, top K. I've explained these in different videos. So they compared with this method, the present paper, ASAP. So they have some slight improvement for example, top K, but a major progress for, if you compare it with diffpo, then it has enhanced state of the art. But it is very similar to SAGPOO. But of course, the standard deviation is smaller, which is better. The same for other data sets like protein. If you compare to diffpo, it has better accuracy and also better standard deviation.